In commercial load calculations for multi-unit buildings like strip malls, determining the total service demand load involves a specific methodology. Unlike residential applications where demand factors can significantly reduce the calculated load, commercial calculations typically require a more direct approach. The fundamental principle is that there is no general demand factor that can be applied to reduce the combined load of all the units within the strip mall. Each unit's calculated amperage contributes directly to the total service demand. The only demand factor that is allowed in commercial work pertains to the neutral portion of unbalanced linear loads, and it applies only when the service amperage exceeds 200 amps. This exception acknowledges that in large services, the neutral conductor's load doesn't simply equal the sum of all the unbalanced loads due to phase cancellations and other factors. To accurately determine the service demand load for a strip mall, firstly, perform individual load calculations for each unit. This involves assessing all potential loads within each unit, including lighting, receptacles, HVAC equipment, and any specialized equipment specific to that tenant's business. It is important to use the appropriate voltage and demand factors for each load type as specified in the National Electrical Code, known as NEC, or local electrical codes. The load calculation must account for both continuous and non-continuous loads, applying the correct multipliers to each. For instance, continuous loads, which are defined as loads operating for 3 hours or more, are multiplied by 1.25 to account for the sustained demand. Secondly, add the amperage values of each unit to determine the total service amperage demand. Once you have completed the individual load calculations for each unit and converted all loads into amperage at the service voltage, simply sum up the amperage values to arrive at the total service demand load. This represents the maximum potential load the service must be capable of handling. For example, let's consider a 7-unit strip mall with the following individual unit amperage values. Unit 1 has 60 amps, Unit 2 has 70 amps, Unit 3 has 80 amps, Unit 4 has 90 amps, Unit 5 has 100 amps, Unit 6 has 110 amps, and Unit 7 has 120 amps. The total service demand load is calculated by adding these values together. 60 amps plus 70 amps plus 80 amps plus 90 amps plus 100 amps plus 110 amps plus 120 amps equals 730 amps. Therefore, based on this calculation, the total service demand load for the 7-unit strip mall is 730 amps. Several important additional notes should be considered. This method assumes that all units are operating simultaneously at their maximum load, which may not always be the case in reality. However, it provides a conservative estimate of the maximum potential load, ensuring that the service is adequately sized. This is a prudent approach to avoid overloading the system. If there are future plans to expand the strip mall or add more units, it is advisable to consider a larger service capacity to accommodate potential growth. Oversizing the service slightly during the initial installation can save significant costs and disruptions in the future if expansion occurs. It is critically important to consult local codes and regulations for specific requirements related to load calculations and service sizing. Local amendments to the NEC or other local electrical codes may have specific requirements that must be followed. Additionally, the utility company may have its own requirements for service connections and metering. Understanding these local requirements is essential for ensuring code compliance and a safe and reliable electrical installation. Addressing the neutral load calculation, which is the only demand factor allowed in many commercial installations, requires a closer look at NEC Article 220.61. This section provides guidance on calculating the neutral conductor load for services. The basic principle is that the neutral conductor must be sized to carry the maximum unbalanced load. For a 3-wire, 120/240 volt single-phase service or a 4-wire, 120/208 volts or 120/240 volts 3-phase service, the neutral load is calculated by considering the maximum unbalanced load between the neutral and any one ungrounded conductor. This unbalanced load is the difference between the load on the most heavily loaded phase and the neutral. For a 4-wire, 277/480 volts 3-phase service, a similar approach is used, but the voltage is different. When the maximum unbalanced load exceeds 200 amps, a demand factor of 70% can be applied to the portion of the unbalanced load exceeding 200 amps. This reduction recognizes that it is unlikely that all the unbalanced loads will be present simultaneously. The neutral load calculation also needs to account for any nonlinear loads, such as those created by electronic equipment, LED lighting, and variable frequency drives. These nonlinear loads generate harmonic currents that can significantly increase the neutral current. The NEC requires that the neutral conductor be sized to carry these harmonic currents. In some cases, it may be necessary to increase the neutral conductor size beyond what is required for the fundamental frequency load. To accurately account for harmonic currents, it is advisable to use a power quality analyzer to measure the actual harmonic content of the load. The results of this analysis can then be used to determine the appropriate neutral conductor size. The size of the service entrance conductors and the overcurrent protection are based on the total service demand load. Firstly, determine the ampacity of the service entrance conductors by referring to NEC Table 310.15b16 or the appropriate table for the conductor insulation type and installation method. The ampacity of the conductors must be equal to or greater than 125% of the continuous load plus 100% of the non-continuous load. Secondly, select the appropriate overcurrent protection device, such as a circuit breaker or fuses, to protect the service entrance conductors. The overcurrent protection device must have an amperage rating that is equal to or less than the ampacity of the conductors. It is also important to consider the available fault current at the service entrance. The overcurrent protection device must have an interrupting rating that is sufficient to safely interrupt the available fault current. If the available fault current exceeds the interrupting rating of the overcurrent protection device, a higher rated device or a current limiting device must be used. The grounding and bonding of the service entrance equipment are critical for safety and proper operation. The grounding electrode system must be installed in accordance with NEC Article 250. The grounding electrode system typically consists of a grounding electrode conductor connected to a grounding electrode, such as a ground rod, a metal water pipe, or a concrete encased electrode. The service equipment must be bonded to the grounding electrode system to provide a low impedance path for fault currents. This bonding is typically accomplished by connecting a bonding jumper from the equipment grounding bus to the grounding electrode conductor. All metal enclosures and raceways containing service entrance conductors must also be bonded together to ensure a continuous ground path. This bonding is typically accomplished by using bonding bushings and bonding jumpers. Proper labeling of the service entrance equipment is essential for safety and maintenance. The service disconnect switch must be clearly labeled to indicate its purpose and the equipment it serves. The panel boards and other distribution equipment must be labeled to identify the circuits and loads they serve. A one-line diagram of the electrical system should be posted near the service entrance equipment to provide a clear overview of the system. All labels must be durable and legible to ensure that they remain readable over time. Regular inspections and maintenance of the service entrance equipment are essential for ensuring its continued safe and reliable operation. The service entrance equipment should be inspected periodically for signs of damage, corrosion, or overheating. All connections should be checked to ensure that they are tight and secure. The overcurrent protection devices should be tested periodically to verify that they are functioning properly. Any damaged or worn components should be replaced promptly. A preventative maintenance program should be established to ensure that the service entrance equipment is properly maintained. This program should include regular inspections, testing, and cleaning. The preventative maintenance program should be documented and followed consistently. In summary, calculating the service demand load for a strip mall requires a careful and thorough approach. Firstly, perform individual load calculations for each unit. Secondly, sum the amperage values of each unit to determine the total service amperage demand. Consider the exception for neutral load calculations over 200 amps. Consult local codes and regulations for specific requirements. Pay attention to grounding and bonding requirements. Implement a regular inspection and maintenance schedule. By following these steps, you can ensure that the service entrance equipment is properly sized, installed, and maintained for safe and reliable operation. Remember to always consult with a qualified electrical engineer or licensed electrician for assistance with complex electrical calculations and installations. These professionals have the knowledge and experience to ensure that the electrical system is code compliant and meets the specific needs of the building. The information provided in this narration is for informational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified professional before making any electrical decisions. It is important to understand the difference between the service demand load and the connected load. The connected load is the sum of the ratings of all the electrical equipment connected to the system. The service demand load is the actual load that the service must be capable of handling, taking into account demand factors and other reductions. The service demand load is always less than or equal to the connected load. It is important to size the service entrance equipment based on the service demand load, not the connected load, to avoid oversizing the equipment and incurring unnecessary costs. When calculating the service demand load, it is also important to consider the diversity of the loads. Diversity refers to the fact that not all loads will be operating simultaneously at their maximum rating. For example, lighting loads may be reduced during the day due to natural lighting. HVAC loads may be reduced during mild weather conditions. Appliance loads may only be used intermittently. Taking diversity into account can reduce the service demand load and allow for a smaller service entrance. However, it is important to be conservative when estimating diversity factors to avoid undersizing the service. It is advisable to consult with a qualified electrical engineer or licensed electrician to determine the appropriate diversity factors for a particular application. The service voltage is another important factor to consider when calculating the service demand load. The service voltage is the voltage at which the service entrance equipment is supplied. Common service voltages for commercial buildings include 120/240 volt single phase, 120/208 volts 3 phase, 277/480 volts 3 phase. The service voltage affects the amperage of the loads. For a given amount of power, a higher voltage will result in a lower amperage. Therefore, it is important to use the correct service voltage when calculating the service demand load. It is also important to consider the voltage drop in the service entrance conductors. Voltage drop is the reduction in voltage that occurs as current flows through the conductors. Excessive voltage drop can cause equipment to malfunction and reduce the efficiency of the electrical system. The NEC specifies the maximum allowable voltage drop for branch circuits and feeders. The service entrance conductors must be sized to limit the voltage drop to within the allowable limit. The length of the service entrance conductors and the amperage of the loads affect the voltage drop. Longer conductors and higher amperages will result in a greater voltage drop. It is advisable to use a voltage drop calculator to determine the appropriate conductor size. The location of the service entrance equipment is another important consideration. The service entrance equipment should be located in a dry, accessible location. The equipment should be protected from physical damage and unauthorized access. The equipment should be adequately ventilated to prevent overheating. The equipment should be located near the point of entry of the service conductors to minimize the length of the conductors. The equipment should be located in a location that is convenient for maintenance and inspection. The coordination of the overcurrent protection devices is another important consideration. The overcurrent protection devices should be coordinated to ensure that a fault on a branch circuit will trip only the branch circuit breaker and not the feeder breaker or the service entrance breaker. Coordination can be achieved by using overcurrent protection devices with different time current characteristics. The coordination study should be performed by a qualified electrical engineer or licensed electrician. The arc flash hazard is another important consideration. An arc flash is a dangerous electrical explosion that can occur when a short circuit occurs in electrical equipment. Arc flashes can cause serious burns, injuries, and even death. The arc flash hazard can be reduced by using arc-resistant equipment, implementing safe work practices, and wearing appropriate personal protective equipment. An arc flash study should be performed to determine the arc flash hazard at each piece of electrical equipment. The results of the arc flash study should be used to select the appropriate personal protective equipment and to develop safe work practices. The power quality of the electrical system is another important consideration. Power quality refers to the quality of the voltage and current that is supplied to the electrical equipment. Poor power quality can cause equipment to malfunction, reduce the efficiency of the electrical system, and increase energy costs. Power quality problems can be caused by harmonics, voltage sags, voltage swells, and transients. Power quality problems can be mitigated by using power quality equipment, such as harmonic filters, surge suppressors, and voltage regulators. A power quality study can be performed to identify and diagnose power quality problems. The energy efficiency of the electrical system is another important consideration. Energy efficiency refers to the amount of energy that is used to perform a particular task. An energy-efficient electrical system will use less energy and reduce energy costs. Energy efficiency can be improved by using energy-efficient equipment, reducing lighting loads, and improving the power factor. An energy audit can be performed to identify and implement energy-saving measures. The maintenance and testing of the electrical system are another important consideration. Regular maintenance and testing can help to prevent electrical problems and ensure that the electrical system is operating safely and efficiently. Maintenance and testing should include visual inspections, thermographic surveys, insulation resistance testing, and overcurrent protection device testing. A maintenance and testing program should be developed and implemented. The documentation of the electrical system is another important consideration. Complete and accurate documentation of the electrical system is essential for maintenance, troubleshooting, and future modifications. Documentation should include one-line diagrams, panel schedules, equipment specifications, and test reports. The documentation should be kept in a safe and accessible location. The training of personnel is another important consideration. Personnel who work on the electrical system should be properly trained in electrical safety and maintenance procedures. Training should include classroom instruction, on-the-job training, and refresher training. The training program should be documented and followed consistently. The compliance with codes and standards is another important consideration. The electrical system must comply with all applicable codes and standards, including the National Electrical Code, the Local Electrical Code, and any other applicable codes and standards. Compliance with codes and standards is essential for safety and reliability. The electrical system should be inspected by a qualified electrical inspector to ensure compliance with codes and standards. The use of qualified professionals is another important consideration. Electrical work should only be performed by qualified electrical engineers, licensed electricians, and other qualified professionals. Qualified professionals have the knowledge, experience, and training to perform electrical work safely and competently. The use of qualified professionals can help to prevent electrical problems and ensure that the electrical system is operating safely and efficiently. These considerations are essential for ensuring that the service entrance equipment is properly sized, installed, and maintained for safe and reliable operation in a strip mall or any multi-unit commercial building. Remember that this guidance is for educational purposes and consulting with qualified professionals for specific projects is essential. The example of a 7-unit strip mall with varying amperage values resulting in a total service demand load of 730 amps is a simplified illustration. Real-world scenarios often involve more complex calculations, taking into account various factors such as motor loads, HVAC systems, lighting types, and specific equipment used by the tenants. It is crucial to gather accurate information about the electrical loads in each unit to ensure the service capacity is adequate. Furthermore, considering future expansion plans is vital. If there is a possibility of adding more units or increasing the electrical demand of existing units, it's wise to oversize the service entrance equipment to accommodate these potential changes. This foresight can prevent costly and disruptive upgrades later on. Always consult with local utility companies and follow their specific requirements for service connections. They may have guidelines on metering, disconnect locations, and other aspects of the electrical service. Accurate record keeping of all calculations, diagrams, and equipment specifications is essential for future maintenance, troubleshooting, and modifications. These records can save time and effort when dealing with electrical issues and ensure that any changes are made safely and correctly. Prioritizing safety and compliance with the electrical codes is paramount. Neglecting these aspects can lead to hazardous situations, equipment damage, and legal liabilities. Remember, a well-designed and properly maintained electrical system is crucial for the safe and efficient operation of any strip mall or commercial building.